Hey there guys, how's it going? Mike coming back at you here with another video on vector calculus. In the previous video, we saw some more examples of working with our multiplication of differential forms. We did some more problems where we figured out the wedge product of two differential forms. In this video, we are going to learn about the other major operation that we need to understand before we get to the big theorem for this section, and really the big theorem for this entire course. We need to talk about the differential operation, or the differentiation operation, or the derivative operation. All these things mean the same thing. We need to learn how do we take the derivative of a differential k form. So if we have a k form, which I'll call alpha, then the derivative of it is denoted by d alpha. And this operation d, which is the differentiation or the derivative, it satisfies the following. Number one is essentially stating how do you find the derivative of a zero form. If you have a zero form, a function of x, y, and z, then df, the differential of f, or the derivative of f, is equal to the partial of f with respect to x times dx, plus the partial of f with respect to y times dy, plus the partial of f with respect to z times dz. Now, this should not be brand new to us. If we think back to earlier on in the course, even going back as far as the chain rule, we saw what happens when you try to calculate the differential of f. We saw this formula popping up in chain rule. We saw this formula popping up as well when we talked about the fundamental theorem for line integrals as well. So this is the total derivative or the differential of our function f. Now, if we had a function of, say, just x and y, so f of x comma y, say that this z term was gone here, then we would simply omit this third term here. This whole thing would be gone, and our differential of f would just be the partial of f with respect to x times dx, plus the partial of f with respect to y times dy. And that's if we didn't have this z term there. So that was property number one. Property number two, suppose we have two k forms, alpha and beta. Then if you want to take the derivative of the sum of these k forms, then that is just the sum of the individual derivatives of those k forms on their own. This should not be a surprise to us whatsoever. It's working in the exact same way as differentiation worked for single variable functions, and partial differentiation has worked for multivariable functions. So this differentiation operator is linear. So number one is something that we have seen before. It's no big shock to us. Number two is something we've basically known for our entire lives. Number three is one that takes a little bit of having to get used to. This is sort of an odd thing in the world of differentiating things. Three is how do we take the derivative of the wedge product of differential forms? So if we have a k form, call it alpha, and we have an L form, call it beta, then the derivative of alpha times beta is equal to the derivative of alpha times beta plus -1 raised to the power k times the quantity alpha times the derivative of beta. So if you think about this, you differentiate the first thing listed, and you take the wedge product of that and the second thing listed. That makes up the first half of your result. Plus, Now look at what kind of differential form the first thing listed is. Look at what kind of K form alpha is. If it's a 1 or a 3 form, then you are going to be multiplying the second term, the second product, by a -1. If it's a 0 form or a 2 form, you are just going to leave it as a plus in front. There's not going to be a -1 in front. And then you have alpha times the derivative of beta. So that guy takes a little bit having to get used to. You can almost sort of think of it as our product rule here. And if you delve deeper into it, you would see that it basically is the product rule. If you look at alpha and beta as just two separate 0 forms, you would see that it is what you get. And for the derivative of a differential form is always equal to 0. And specifically in terms of our basic 1 forms, dx, dy, and dz, if you take the derivative of each of these guys on their own, you will just get 0. So as a little follow-up note before we get to our first example, if you have a K form where K is less than 3, and we're not talking about our basic 1 forms or our basic 2 forms. So not just dx or dy or dz, or our cyclic pairs dx, dy, dy, dz, and dz, dx. If you exclude those guys, and you have a 1 or 2 form or a 0 form, and you take the derivative of that K form, you are going to get a K plus 1 form. So if you take the derivative of a 0 form, you get a 1 form. Differentiate a 1 form, you get a 2 form. Differentiate a 2 form, you get a 3 form. If you differentiate a 3 form, then you're just going to get 0. So note that and use this as a little helpful tool such that when you have to differentiate one of these K forms, know that you should get something that is a K plus 1 form. So here's our first sample. Start off light, start off easy. We give you a differential 0 form here, and you have to find the differential of f, or the total derivative of f. F of xyz is 3 times y cubed plus z, that quantity squared, plus the tangent of e to the x. By property number 1, df is the partial of f with respect to x times dx. Differentiate the first term, you just get 0. It's all a big constant. And then times the derivative of that tangent of e to the x. Nice little Calc 1 chain rule there. Get e to the x times secant squared of e to the x. So that guy times dx, plus the partial of f with respect to y times dy. Partial of f with respect to y, you're only going to get something from that first term. That's a basic chain rule type problem for partial derivatives. Get 18y squared times y cubed plus z, all times dy. And then plus the partial of f with respect to z times dz. Again, you're just going to get something from that first term. Multivariable chain rule partial differentiation going on there. So this is pretty basic, pretty straightforward, just a little something to help get our feet wet and get us set for jumping in to the deep end of differentiating these differential forms. So next example, we have a differential 1 form. We are going to find what the derivative of this guy is going to be. So I left these in terms of arbitrary functions of x, y, and z, and we do that on purpose because the main purpose of what we're going to use these things for, we're not going to do these things with specific things being substituted in for p and q here. We're just going to leave it in terms of general 0 forms, p, q, r, f, g, h, whatever. So we're going to find d alpha. Alpha here is p dy plus q dz. So d alpha, the derivative of alpha, is equal to the derivative of p dy plus q dz. We said by property number 2 that this differentiation operator was linear, so it's d of p dy plus d of q dz. Well, p dy is the same thing as the wedge product of p and dy. Q dz is the same thing as the wedge product of q and dz. Now, we use property number 3. We use that property that we have to take a little bit of getting used to, and the more we work with it, the more we get used to seeing how we use it. The derivative of p dy, recall how this works. We take the derivative of the first thing listed in our wedge product times the second thing. So that gets us that term there. Plus, now the question is, do we need to multiply by a -1 or not in front of this term here? Well, what we have first listed here is a 0 form, and it's -1 raised to the power k, raised to whatever type of form we have. -1 to the 0 is +1, so we leave the plus in front of our second term. And now this d goes to the second term that's listed. So that's why we have the p times the d of dy. So these two terms we get as a result from the first term listed in the line above. We're going to do the same thing with the second term here. D of q times dz gives us dq times dz. And now, again, it's a plus for the same reason that it was a plus in the second term in this line here on the bottom. Q is a 0 form, -1 to the 0 is a +1. And then we get q times d of dz. Now, let's look at some of these terms that we have here. I see in the second term we have a d of dy. By property number 4, we saw that d of dy is equal to 0. So we're going to get a p times 0, or a 0 here. And just by the same reasoning over here, we have a d times dz, or d of dz, I apologize. D of dz is a 0, and q times 0 is going to be 0, so this whole thing is gone. So we're left with the dp times dy plus the dq times the dz. We're going to take the differential of these 0 forms p and q, and when we do that, we get our next line down here. We get partial of p with respect to x times dx, plus the partial of p with respect to y times dy, plus the partial of p with respect to z times dz, all that times dy. And then plus, by a similar reasoning, the entire second term there on this bottom line. I'm now going to multiply this dy into each of my terms here, and I'm going to likewise multiply my dz into each of my terms here. This gets us down to this line here. We have the dx times the dy, dy times dy, dz times dy, so on and so forth. Now, we know that if we take the wedge product of any one of our differential forms with itself, dx times dx, dy times dy, or dz times dz, it's always going to give us 0. So this whole thing is going to be 0, and so is that whole thing. That's going to just be a 0 as well. So now we're left with some two forms here. We have dx's and dy's, dz's and dy's, dx's and dz's, all these things here. Now we just have to put these two forms, these basic two forms, in the proper cyclic pair order. Again, it's dx dy, dy dz, and dz dx. This right here is going to be a dx dy. That's fine. This would be a dz dy. That's not right. We need to switch these guys. And when we switch them, we multiply by a -1. This would be a dx dz here. That's not right. We have to switch these guys as well. When you switch them, you multiply by a -1. And this guy right here is a dy dz. That's one of our correct cyclic pair orders, so we leave that as well. We recombine like terms, and we get, in the end, this guy right here. We get our final result. Partial of p with respect to x times dx dy plus partial of q with respect to y minus the partial of p with respect to z times dy dz minus the partial of q with respect to x times dz dx. Now, note that this is a result that we would have known from the very beginning before we went through this entire process. Note that this is a reasonable answer. We started off with a one form, we differentiated it, which means we know that we should be ending up with a two form of some sort, and we do indeed end up with a two form. So this is a very plausible answer, and going through this step by step, we see that this is what we should get. So this is the other, this is one more type of differentiation slash derivative problem we could see for differentiating these differential forms. Last example that we're going to see here in this video, we're going to take the derivative of a two form. And we're going to see that there is a bit more work involved here, but we'll see what it comes out to be in the end. So alpha is p of xyz times dx dy plus q of xyz times dz dx. And we're going to find the differential or the derivative of alpha, this two form here. Now, we know that we should come up with a three form. So we know that our final answer should be some stuff times dx dy dz, or any equivalent cyclic order of that. So, the differential or the derivative of alpha. Again, we're starting off in the same kind of way as we did with our previous problem. We're going to break this up at the plus sign and take the sum of the derivatives of these two things here. The derivative of p times dx dy, derivative of p times dx dy, plus p times the derivative of dx times dy. Again, the first form that we have listed here is a zero form. -1 raised to the power 0 means that it's a plus that stays in the middle here. And in this term here, I had to separate out the dx times the dy here to see what we're going to get. Now, when I say I have to, I actually mean I don't really have to, but I just want to show you an example in detail to see why we get what we get. I think you can probably guess what we're going to get as a result of this, hint, hint, 0, but let's just go into a little bit of detail for the sake of understanding why this is what this is. We've been trying to understand why things are what they are before, so let's just keep on the same path. And now the derivative of the second term, d of q times dz dx, same reasoning process. gives us dq times dz dx plus q times d of dz times dx here. Now, I want to look at these terms here and see what these things turn into. Specifically, looking at the derivative of the wedge product of our basic one forms. D of dx times dy is going to be d dx times dy, and now it's minus, because these are differential one forms, so it's -1 to the first power, so minus dx times d of dy. So this one thing gives us these two terms here. And by a similar fashion, q times d of dz times dx gives us these two terms here. That d of dz times dx is going to be d of dz times dx minus dz times d of dx. Well, from property number 4 in our rules of differentiating these differential forms, d of dx, d of dy, and d of dz are all zeros. So this guy is a 0, this guy is a 0, that guy is a 0, and that guy is a 0 as well. And wedge products of anything in 0 are zeros, and 0 minus 0 is 0 as well. So this entire thing here, these entire terms, are going to be gone. So all we're left with now is the sum of two terms. This dp times dx dy plus the dq times dz dx. We write out the differential of p and q, giving us this line right here. P sub x dx plus p sub y dy plus p sub z dz, and q sub x dx plus q sub y dy plus q sub z dz as well. We now multiply our differential two forms into each of these terms. There and there as well. And that gets us to this line right here. Now, hopefully by now we're a little bit more comfortable overall with the wedge product and being cognizant of the properties showing up and how we can use them. Anytime you see two basic one forms showing up in the same term, like we have happening here, we have a dx showing up twice, we have a dy showing up twice in here, and there's other cases where we have it going on here, here and here, here and here. If you see the same basic one form showing up twice, when you take that wedge product, that whole thing is just going to be 0. So all these terms here are going to vanish. So all we're left with are these two terms. Partial of p with respect to z times dz dx dy. Now this does follow our cyclic order. So we can take that dz dx dy, we can leave it as it is, or we can just rewrite it as dy dx, or as dx dy dz, my apologies, and it's going to be the same thing. There's no minus sign that we have to multiply in there. And in our second term here, we have q sub y times dy dz dx. That also follows that cyclic order, so we can also rewrite that as dx dy dz, and it doesn't change anything. So what we're left with in the end is the 3 form, p sub z plus q sub y times dx dy dz. And as we said back at the beginning of this problem, this is what we would plan on getting, because we started off with a 2 form. When you take the derivative of a 2 form, you get a 3 form, and there's only one way to represent a 3 form. Something times dx dy dz. So these are the examples that we go through in this video on the differentiation of these differential forms. In the next video, we're going to see some more examples of differentiating differential K-forms. If you have a question or comment, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.